Hey everyone, this is Sheetal here, and today we're going to talk about ventilation and perfusion in the lungs. So let's start. So the first thing is the ventilation rate, which is nothing but the volume of gas inhaled and exhaled from the lungs in a given period of time. Now, if we are changing this given period of time to a minute, that's nothing but the volume of gas inhaled and exhaled from the lungs in a minute, then that's called as minute ventilation. And this is completely different from alveolar ventilation, which is nothing but the amount of air that reaches the alveoli in the lungs for gaseous exchange per unit time. So, where like the minute ventilation is the amount of air that enters the lungs in a minute, and alveolar ventilation on the other side is like amount of air that reaches the alveoli in the lungs for gaseous exchange per unit time. So they're two different things, and in this video, we'll be talking more about like the air that has entered the alveoli for gases exchange. So, ventilation in the lungs. So, ventilation in the lungs is greater at the base than in the apex. This is mainly because of gravity. Like, because of gravity, the weight of the fluid in the pleural cavity increases the intrapleural pressure at the base. So, the intrapleural pressure at the base is like more higher, and they exert this pressure, higher pressure exerted on the alveoli in the base causes them to stay like less expanded, and they have more compliance, that is their ability to expand is much more than that of the alveoli that are present in the apex. Like the ones in the apex are already like expanded, they're big alveoli and they're expanded, and they can no more further expand for like when there is air, that when air enters. Whereas the ones in the base, they have like this, they are like less expanded and they have higher compliance. It's mainly because of this pressure exerted on them. So because of which they have the ability to expand. So when air enters, they can expand and accommodate more air, and therefore there's more ventilation at the base than that of the apex. Then perfusion. Perfusion is also greater at the base of the lungs. Again, this is due to gravity, where the blood is being like pulled down towards the base. So that's ventilation and perfusion, and we assume that like both of this is assuming that the person is in an upright position. If the person is like in a supine or like maybe in a prone position, then it might be quite different. So this is like assuming he's in an upright position. And now let's talk about VQ ratio. So VQ ratio is nothing but ventilation perfusion ratio. That's like ventilation here is the air that reaches the alveoli, and perfusion is the blood that reaches the alveoli via the capillaries. So the VQ ratio is the ratio of the amount of air that has reached the alveoli per minute to that of the amount of blood reaching the alveoli per minute. So the average VQ ratio is 0.8, but it is different in different regions of the lungs. So it's not like really like standard, or like like 0.8 is just an average. It could be more than one in certain regions of the lungs. It could be less than 0.8 in other regions of the lungs. So it's really dependent on the regions. So now I'll just talk about like VQ ratios in like different regions of the lung. So this is like divided into like zones. Like we can divide the lung into like different zones. So that's the west lung zone. So where like we divide them so that we can identify the VQ ratios in different regions of the lungs. So the first zone is like the apex, where the alveolar pressure is higher than that of the arterial pressure and the venous pressure. Now the alveoli in this region are really expanded, and like they exert pressure on the blood vessels flowing in that region, or the capillaries that are like there beside the alveoli, like they are like compressed, or like they collapse because of the increased alveolar pressure, and because of this there is a decreased blood flow in these regions, or like maybe decreased blood flow, or like no blood flow at all. So because of this, like the VQ ratio in this region is very high. That is, there's good ventilation, but there is decreased perfusion, or like no perfusion. So if there's no perfusion, then in such kind of conditions, it's like infinity there. Like the value, like the VQ ratio is infinity. But if there's perfusion, then it's like VQ ratio is more than 1. And that's zone 1. And there is zone 2. In this region where the alveolar pressure is lower than that of the arterial pressure but higher than that of the venous pressure. So here, like the VQ ratio is approximately like equal to 1. Like it's not like it can differ like a bit up and down, but it's approximately equal to 1. So here there is like the alveolar pressure is lower than the arterial pressure. So therefore there is some amount of perfusion that takes place. There is alveolar pressure that's exerting pressure on the blood vessels, but it's not that high enough to like compress it or like completely collapse it, but it's like proper. So because of that there is good amount of ventilation and as well as perfusion as well. So therefore the ratio is like approximately equal to 1. That is nothing but the amount of air that has entered the alveoli for gases exchange is equal to the amount of blood that has amount of blood in the like the blood flow rate in that region. And now there is zone 3. So in zone 3, which is like in the like close to the base. So here here the arterial pressure and the venous pressure is higher than that of the alveolar pressure. So therefore, like here there is like increased perfusion. Like we have to consider the fact that both ventilation and perfusion are highest at the base, but the perfusion, but when comparing the ventilation and perfusion values, the perfusion value is so high, is like comparatively higher than that of the ventilation. So therefore the ratio here would be like less than 1. That is nothing but increased perfusion when like both of them are increased, but increased perfusion in comparison to that of like ventilation. So that's basically like the lung zones. And so that's what the ideal VQ ratio is, like 1, which is meaning that the same amount of air and the blood flow, like the amount of air is equal to the blood flow. But this is just like the VQ ratios greater or smaller than 1 represent a VQ mismatch. The ratio is higher at the lung apex, that's like approximately 3, and lower at the base of the lungs, that's like approximately equal to 0.6. In comparison to the middle portion of the lungs, where it could be approximately equal to 1. And now we tell all this again considering to the fact that the person is in an upright position. So when we take the average of these three, like the three zones, we get the average VQ ratio as 0.8. Also, like now this is generally like a physiological this is like physiological for a human being for a healthy lungs, but VQ ratio can change in the lungs, like depending upon the pathology involved in the lungs as well. Like if there is an obstruction, if there's an obstruction in the capillaries or in the blood vessels, then there could be decreased perfusion to that area, and because of that the VQ ratio might increase. On the other side, if there's some issues with the alveoli, or the ventilation, like some kind of an obstruction in the airways or something like that, because of which there's decreased ventilation, then the VQ ratio might decrease because of that. So with that, we can use that as a diagnostic parameter for like different pathologies. So now we can talk about the blood flow through the vessel. So here we get to see that the like in the West Zone 1, there's almost like no perfusion because of that, and there's no perfusion. And in West Zone 2, there is intermittent blood flow, and in the third zone there is like good amount or like increased blood flow. So that's what this graph talks about. It talks about like um, the blood flow depending upon like different zones of the lungs, and the y-axis here is just the height of the lungs. So now we are going to talk about physiological dead space or total dead space. So dead space is nothing but the volume of ventilated air that does not participate in the gaseous exchange. There are two types of dead space. One is the anatomical dead space, and the other one is the alveolar dead space. So when we combine them both, we get the total dead space or like the physiological dead space. So the anatomical dead space is like the volume of air that fills the conducting area, like the airways, like that's like made by the trachea, bronchi, and all those. And on the other side, we have the alveolar dead space, which is nothing but regions like certain alveoli are like very well ventilated, but they are not perfused. Like we saw in zone one, where there is especially in the apex region, where there is like decreased perfusion because of pressure, like a decreased perfusion or collapsing of the vessels, collapsing of the um, blood vessels because of like increased pressure from the alveoli. So in such kind of places, there is like alveolar dead space. In a healthy lung, anatomical dead space is almost equal to the physiological dead space, but alveolar dead space is like really negligible. So now we'll talk about physiological shunt. So physiological shunt is the total amount of shunted blood per minute. Um, per minute. That's basically what a physiological shunt is. So it is nothing but like the blood from the heart, like from the that's pumped out of the right ventricle, bypasses the pulmonary circulation and drains into the pulmonary vein. So this kind of condition could occur either because of like deoxygenated blood from the bronchial circulation, which does not which does not get oxygenated in the lungs. Rather, it directly drains into the pulmonary vein and like goes back to the heart for systemic, like getting pumped to the systemic circulation. And it can also occur when like when we stand up or when we are in an upright position. More blood goes to the base of the lungs while relatively less air gets there. Like we have to remember that the ventilation and perfusion in an upright individual is always highest at the at the base of the lungs, but like the ventilation is comparatively lower than that of the amount of perfusion. That's what we need to like in comparison to perfusion, the ventilation is lower. So in such kind of cases, like when there is like high blood flow and comparatively smaller ventilation, a small amount of blood fails to become oxygenated. So in such kind of conditions, we can also see a decreased vq ratio, like we saw in the case of like zone 3. So yeah, we've come to the last slide of this video, and so just a revision. So decreased ventilation leads to shunt perfusion, which is also called as wasted perfusion, and a low VQ ratio. In areas with no ventilation, where the ventilation is zero, then VQ ratio equals to zero. Decreased perfusion leads to dead space ventilation, like wasted ventilation, with no perfusion left. Like when the perfusion value is zero, VQ value ratio, VQ ratio equals infinity.